Food as fuel. These two molecules have lots of bonds and is a good source of energy. When electrons have a small nucleus and the electrons are close to the nucleus, then they can be pulled away and increase the potential energy. So looking at this diagram, you can see that if you can take, this is the lowest energy level, you can take an electron and it can absorb some energy and go to the higher level or go to even a higher level. At some point, it'll lose that energy and come back down to what's called a ground state, which is a more stable state. So the size of the nucleus is going to influence how much the potential energy of the electron has, and how strongly the electron is attracted. So an electron is going to be more strongly attracted to a large nucleus because there's more charges in there than a small nucleus. In a carbon-hydrogen bond, you have electrons that are not quite in the center. They're about in the middle between the carbon and the hydrogen. And the electrons have a lot of energy. And these electrons can be pulled closer to the more attractive nuclei in a process that releases energy. So if an item is more electronegative, then it can attract other electrons. This is important in the electron transport chain, where oxygen is grabbing electrons because it has a strong ability to attract other electrons. So if we look at carbon dioxide here, between carbon and oxygen, oxygen is the more electronegative, so they can draw the electrons toward themselves. And as those electrons are pulled away from an atom towards the electron, they lose some of the potential energy, which can be released during bond formation. So just the basics, a loss of an electron is oxidation and a gain of electron is reduction. So Leo the lion goes grr. Often electrons become bonded to oxygen because it's quite electronegative. So we call it, so in the electron transport chain, this is called the final electron acceptor. So any atom or molecule that gains electrons is called an oxidation agent because it causes electron loss. So in the electron transport chain, oxygen would be that. In redox reactions, sometimes electrons transfer completely from one atom to the other, and sometimes they remain shared. So in methane, for example, they have very similar electronegativity values, so those electrons are shared pretty equally, whereas in CO2, which was on the previous slide, the electrons are drawn closer to oxygen. In this case, then the carbon has experienced a partial loss of electron, which is an oxidation. So if you were to look at oxygen and water, then oxygen shares electrons equally because, of course, it has the same electronegativity each. And then oxygen, so if something is reacting with methane, then oxygen can react with hydrogen from the methane. The oxygen now pulls electrons closer to itself, and then the oxygen molecule has been reduced because it gains electrons. And then as the electrons come closer to oxygen, then energy is released. So here's the equation that I was talking about. Carbon and hydrogen, you can see they're almost equidistant. Oxygen, they're equal. Oxygen is pulling electrons closer to oxygen than carbon. And you can see the reverse is happening here. So here we have the combustion of glucose, where over here the oxygen is gaining electrons, which is a reduction, and this glucose is losing electrons in an oxidation. So the oxidation of fuel molecules like glucose releases some of the potential energy that's stored in bonds. Remembering again that the reduction is addition of hydrogen or the removal of oxygen. So here we can see hydrogen's been added. When hydrogen's added, hydrogen has one proton and one electron. So you've essentially added, when we add two hydrogens here, we've added two protons and two electrons. This is just the same thing, bigger. This is just an overall way of looking at it. Your methane, your carbon becomes oxidized because there's been a loss. These hydrogens have combined with this, taking their electrons with them. If carbon, it loses electrons, it becomes oxidized. That means that the oxygen gains electrons and becomes reduced. If you have a rapid oxidation or burning of fuels, oxygen gas does the oxidation. Glucose can undergo combustion and burn, where you have the transfer of electrons, which produce carbon dioxide, water, and energy. A lot of thermal energy is released if that's done that way, but the alternative is a controlled oxidation. Obviously, we don't want a huge release of energy in our bodies, so instead of having one big reaction, you can have a slow capture. The advantage is that instead of losing it all as thermal energy, that energy can be used to do other things. So in cells, the oxidation of glucose happens through a series of enzyme-catalyzed reactions. So in each step, a tiny amount of energy is released, followed by the absorption of a small amount of activation energy from the environment. So the energy that is released from these enzyme-mediated reactions transfers energy to energy-carrying molecules that are used later on. Whether it happens really fast or slowly, they are both exergonic reactions, meaning that they release energy. But the difference is that if you have a controlled oxidation, then you can have an efficient harnessing of the energy, which can be used to generate ATP and control metabolism and stuff. So here is if we burned sugar, like when we saw the gummy bear sacrifice, you add in some oxygen, and then you put in a little bit of energy, and you get a huge amount that's released, and you have some lower energy products, more stable products. Instead, in your body, you would have your sugar and your oxygen. You'd have a lot of small little steps, and then all of this energy is transferred to carrier molecules that can harvest that energy for later use. This is just the same thing, bigger. So what are these energy carriers? So the most important redox reaction is when glucose is oxidized to form CO2 and water. So enzymes called dehydrogenases pull electrons from food molecules and transfer them to energy carriers such as NAD+. Energy carriers are shuttles. They're a coenzyme. During cellular respiration, these dehydrogenases remove two electrons and two hydrogens from a substrate molecules and transfer the two electrons, but one hydrogen to NAD+. The other hydrogen goes into the cytosol. So NAD+ is reduced to NADH without any very big losses. And the potential energy that's carried with this energy carrier helps with ATP synthesis. So here is the NAD. And then once it has 2 electrons and a hydrogen, then that's it in its reduced form. And that's a closer look at it.